In a previous video, we talked about the idea of doing what was called a best fit line. And one of the things that we discussed about best fit lines in that video was the reality was it wasn't really the best. So I have some good news and bad news. The good news is there are mathematical methods that we can use to find a better linear model than the so-called best fit line. And more accurately, it may make a more accurate prediction rather than what we've done earlier in this lesson. Now eventually you're going to be able to use a calculator to help you do it, and by eventually I mean almost right away. The bad news is I'm at least going to show you sort of the formulas that go with this at first, and they're not very pretty, as you can already maybe see on the screen. So what do you need for the equation of a line? Well, of course, you need two things. You need a slope and you need a y-intercept. Okay, that's the good news. Now the bad news. These formulas right here, which would make anybody go and scream in absolute terror. Okay, now these big E-looking things, they're a sigma, which is for summation. Please pardon me as my dog is walking around in the background here. Okay, so I've heard your gasps of horror here on this and can't say that I blame you. So as I get this page moved up here to show you a quick example, I'm probably going to skip over most of this because, truth be told, we really don't need to go through the whole idea of how the sausage is made here. Okay, so I'm going to jump to the next page and I'm going to do just kind of do a quick example, but use my calculator. Okay, now I want to point out to everybody that this data is in your notes, and the steps for doing this in your TI-84, they are in a video that's linked on our Canvas site already. So it'll be somewhere on that 1D page where you'll be able to look. Now for our crowd here, that sigma and those ugly formulas, they're just not a very practical way of calculating the least squares line or the linear regression line. If you've only got 5 data points, it's not so bad. But if you've got more than 5, like what we do in this table right here, then yes, you're probably going to want to use a calculator just to save a lot of time and not do very many painful calculations. Okay, so this is an accidental death rate, which I assume is per 100,000 maybe over the course of the 20th century. And we have data from 1910 all the way to 2000. So what I did for this data was I changed the years so that way every year was in relation to the year 1900. So it's like this first ordered pair that's right here. This had an ordered pair of 10 and 84.4, and then 20 and 71.2, and so on and so forth. Okay, and what I did was I put this into my own calculator, and I came up with a least squares line. And what this least squares line does is, if you think about a scatter plot, it's going to create a line that's going to have the minimum distance away from the data. So this is truly the least squares line, is the one that comes as close to the data as it can. When I did this in my calculator, my TI-84, this is what I came up with. I came up with y is equal to negative 0.5. I'm going to make it negative 0.56x plus 90.33. Okay? And that is going to be the accidental death rate over time according to this particular model. And again, I've got directions down here for you to be able to do this on there. I'd go watch the video that is on our Canvas page before jumping into trying it on your own. And obviously, sing out if you got any questions. Okay? So that's our least squares line. And here comes an interesting question. It says, what do you expect the accidental death rate to be in 2030? Well, that means I have to use my x as being 130. So I am going to go ahead and type that into my calculator. and see what I come up with here as far as the, as far as this goes. So 0.56 times 130, and then plus 90.33. You're probably thinking, just hurry it up and tell me what it is. Okay, so I will tell you. 17.53. Now, I want to make a quick comment about the data itself here, since it reflects accidental death rates. Obviously, there's been a lot of advances in safety over the course of time, everything from safety belts to motorcycle helmets and all sorts of other things. And we know that it makes sense to always wear a helmet even when you ride a bicycle, and protective gear when you're skateboarding and things like that. So it's not a surprise that the accidental death rate has come way down. I mean, we've come a long way from trying to stop toddlers from sticking their fingers into the sockets too. So the fact that the accidental death rate continues to go down by this model, if that were the case, it wouldn't surprise me, only because we keep innovating in the area of safety. All right, now, down here at the bottom of this page, we start talking about a way to show whether or not our model is accurate. And this particular way to show whether the model is accurate is called the correlation coefficient. And if you thought the previous formulas for slope and intercept were evil, this one is just downright diabolical, and I will never ever make you do this by hand, because there's just no need to do it by hand, okay? But just to kind of clean this up, the N stands for the number of data points, and you're adding up all the X's and all the Y's and some combination of X times Y, and then the squareds, and then maybe you're squaring this off or squaring that off or standing on your head. The bottom line is this. This formula always evaluates to a number from -1 to +1. Okay? So, going on to the next page here, if your R value is closer to -1 or +1, then the model is a good fit for the data. And then closer to 0, the model is a poor fit for the data. And if I were to ask you to make a comment on whether or not the model is a good fit based on certain things, I would say to you, that's what you want to say. You want to basically comment if it's a good fit or a poor fit based on the R value. Again, closer to 1 or -1 is good. Now, for our example with the accidental death rate there, the R value happens to be 0.93. Since that's pretty close to 1, it's probably a pretty good model for the data. Actually, I should say -0.93. I'm sorry. Now, the reason why it was negative is because the slope was negative, so the R value is negative. On your calculator, it is very likely that you are going to see R squared is equal to something and R when you go to do this. For the purposes of our class, the R value is the only one you're interested in. Okay? So that's our coefficient of correlation. You can just pretty much ignore that R squared. All right, folks, I hope this is a good summary for you, and we will be working a lot with this concept both on the TI-84 and on Desmos, and this is what you will be doing to help you determine if your airfare when you fly is a good model, whatever airfare prediction you come up with. And we'll talk about that in the project in just a few moments.